Hello guys, welcome to the machine design world. This is Keval Patil and today we are going to see design of spring under bearing loads. In last video we have seen the full problem of design of bearing load. Now we will see further problems. Okay guys, so let's move to the first problem. Design of spring under bearing load. So problem reads, a closed coil helical compression spring is subjected to an axial load varying from 5 kN to 6.5 kN. So again, helical compression spring, again load having 6.5 kN, so 6500 Newton, and minimum load is 5 kN, that is 5000 Newton. At a frequency of 20 cycles per second, nothing but 20 Hertz. Alright, the spring rate is 70 Newton per meter. What is spring rate? It is nothing but spring stiffness, so it is nothing but Q, 70 Newton per meter. Design of spring force. Design a spring for factor of safety of 1.8. So factor of safety is already given. Last time we assumed it for 1.5. Assumed as 1.5. And the following properties of material. SU in terms of wire diameter 2000 divided by d raised to 0.17. SY, then S dash SE. So SU is nothing but sigma U or sigma UT, that is nothing but ultimate tensile strength. We are using this notation because it is in PSG. Then tau Y, torsional yield strength. So SY is nothing but tau Y, and S dash SE is nothing but SNO or tau O. We are using this notation tau O. Sometimes they give SNO, sometimes they give S dash SE, so it is tau O or tau 0, and this is 3 notation we are using. Okay, it is nothing but endurance shear strength. Again there G is equal to 80,000 Newton per mm square is given. So this is the given data. Let's move to the problem. Right. So now first we find amplitude load and mean load. So PA is equal to amplitude load, that is P max minus P mean divided by 2. So it is 6500 minus 5000 divided by 2. So it is 750 Newton. Okay. Then P mean is equal to P max minus plus P mean divided by 2. So 6500 plus 5000 divided by 2. So it is something 5750 Newton. This we have already seen in the last sum. Same I am copying, nothing difference. Okay. So then after this we find Wall's stress factor. So Ks is equal to 4C minus 1 upon 4C minus 4 plus 0.615 upon C. In last sum we were writing like amplitude, then amplitude load, mean load, assume this, assume that, wall stress concentration factor. Every time we were using heading. It was for your convenience or to understand in your exam. You don't have to read all that, directly start like this. Okay, now assuming C, that is d by d is equal to you can consider any. I'm just considering 6. Okay, it varies from 4 to 12. Okay, so Ks is equal to 4 into 6 minus 1, 4 into 6 minus 4 plus 0.615 upon 6. So you will get 1.2525. Now we know for 1.25 Ko value is on PSG 7. Here it is given curvature KO value for C6 is 1.15, and the relation of KSH and KO for KS is equal to KSH into KO. Okay, so it is 1.15. You have to mention the PSG page number, and it is something PSG 7.102. Okay, now you know the relation. Ks is equal to KSHO into KO. From this KSH is equal to 1.25 divided by 1.15, and you will get value something 1.0891. Alright, so now we having all these values, so we can move to the amplitude stress and mean stress. So here are the values for amplitude, formulas for amplitude stress and mean stress. We will use this formula. As we don't know the diameter d, we will use this formula, then we will use this one. So amplitude stress tau e is equal to 8 ks pa c divided by pi d square. Nothing but 8 into 1.2525 into 0.75 into 10 raised to 3, or you can consider 750 into 6 divided by pi into d square. We don't know the value of d square. You will get something 14352 upon d square. Alright, then tau mean value as 8 ksh, p mean c, this is c, upon pi d square. So it is 8, ksh value is 1.0891 into this one is 5750 into 6 divided by pi into d square, and you will get value as 95681 upon d square. This is also in Newton per mm square. This is also in Newton per mm square. Now you will use what to use? Factor of safety. Now factor of safety is given, right? We know that in question factor of safety is given as 1.8. Okay, earlier problem it wasn't given, we consider it 1.5. Okay, so formula is n is equal to tau m minus tau a divided by tau y plus 2 tau a upon tau 0. Okay, so now 1 upon 1.8, what is tau m value? Tau m value is 65981, so I'm just 95681 upon d square minus tau a value is 14352 upon d square whole divided by sigma y. So sigma y value was 1200 upon t raised to 0.17. So 1200 t raised to 0.17 plus, so again 2 into 14352 upon d square divided by d0. d0 is nothing but 600 upon d raised to 0.15. So 600 upon d raised to 0.15. So put this value in the calculator and find the value of d. So you will get value of d as, so after calculating you will get value as 18.24 mm. Remember that this equation won't fit in the solve for x method in calculator. For that you have to simplify this, just this having common denominator, so you can write as this minus this upon d square. So just make this subtraction before only and then put in the calculator. Again you can multiply this and then you can put in the calculator. For this you just use d raised to 0.17, don't use 0. For this d raised to 0.15. So that now you having d 18.24. now this is not in the standard diameter in the PSG. See, in PSG page number 7.104 we are having large diameter is 13. It is not in PSG, okay, but we have to use this only. Okay, we can say like it is special purpose spring. Alright, now all other steps like mean, call, diameter and all, they are same like earlier, so I'm not going for them. So remaining part is same like previous problem. Alright, so let's move to the second problem. Before going to the second problem, there is one note. In some problems, they don't specify values of tau 0 and tau I, or they don't give these values. And in some problem, they say like choose the appropriate material or choose the material for the spring. Okay, so here is a selection criteria of spring. It is given in Bhandari book. Okay, so if you go to the PSG 7.105, then you will find three types of material for the spring. Okay, first is steel wire, unalloyed, cold, drawn. Second is spring steel, oil hardened and tempered. Third is spring steel for moderately elevated temperature. In Bhandari, so it is having 4 grades, it is having 2 grades, SWW, and it is having again 4 grades. So in Bhandari, these two properties are given. Okay, you have to remember any one. You can remember this, you can remember this. Okay, I am for cold drawn steel wire, that is first grade 1 to 4. You having tau 0 at 0.22 into sigma u and tau y 0.42 into sigma u. For oil hardened and tempered steel wires, we have tau 0 is 0.22 sigma u and tau y is 0.45 sigma u. It is not given in PSG, but in case it is not given in the problem, then you have to consider this. And remember this, oil hardened and tempered steel wires. So for my material is this one, right? Okay, so let's move to the next question. Now the next question reads, a helical compression spring is subjected to load varying from 0 to maximum of 9 kN. So again it is varying load. First is 0 and then it is 9 kN. So P mean is 0, P max is 9000 Newton with corresponding deflection of 90 mm. So 0 load, there won't be any deflection. For 90 mm it will be 90 mm. For 9 kN it is 90 mm deflection. So y is equal to 90 mm. Consider average service. Okay, average service it is given. Okay, spring steel having ultimate tensile strength sigma ut 2000 upon d raised to 0.16. This is nothing but value of sigma u, and g is also given. Design the spring. So now in this problem we are not having values of tau 0 and tau y. So we have to find those values using this empirical relations, or relations you can say. Alright, so now let's start with the problem. First of all, we are having P mean tau amplitude, or P amplitude is equal to P mean minus P max minus P mean divided by 2. So it is nothing but 9000 minus 0 divided by 2. So you will get 4500 Newton. And here you will get sigma mean is equal to P max plus P mean upon 2. So again you will get same value, that is 4500 Newton. Then we find Ks is equal to 4C minus 1 upon 4C minus 4 plus 0.615 upon C. Okay, now assuming C is equal to 6. Alright, so it is given in PSG 7.100. This formula is given. Alright, so now it is nothing but, we know this, after putting 6 we will get 1.2525. we just not saw. Then we select K0 as 1.15. again it is from PSG 7.02. Okay, so we know the relation Ks is equal to Ks is into Ko. This is also given in PSG 7.102 itself. From here we will get Ksh as 1.0891. So similar to the last problem. Okay, now we'll move to the next, that is finding tau A and tau mean. So tau A is given as 8 ks PAC divided by pi d square, and it is given in PSG 7.102. So it is nothing but 8 into 1.2525 into this is 4500 and 6 divided by pi d square. You will get value as 86115 divided by d square Newton per mm square. Then tau mean is equal to 8 ksh P mean C upon pi d square. This is also given in PSG 7.102. 8 into, see, only this much change, so it is 1.0891 into 4500 into 6 divided by pi into d square, and you will get value as 74881 divided by d square Newton per mm square. Okay, then we know the formula of factor of safety. It is also given in PSG 7.102. Okay, it is also given in PSG 7.102. And the formula is 1 upon n is equal to tau m minus tau a upon sigma y plus 2 tau a upon sigma g. The problem is we don't have this value, so we have to assume the material and we have to find those value. So assuming oil hardened and tempered steel wires, okay, and tau 0 is 0.22 sigma u. So we know the value of sigma u. It is given in question. Okay, so just putting that value 0.22 into 2000 upon d square, you will get value as 440 upon d raised to 0 is 0.16 Newton per mm square. Similarly, tau y is equal to 0.45 sigma u, so it is 0.45 into 2000 upon d raised to 0.16 is equal to 900 upon d raised to 0.16 Newton per mm square. Now put all this value of tau a, value of tau m in this equation. Also put n is equal to, you can assume, okay, assuming n is equal to 1.5, and 1.5 tau m tau u value we are having, then sigma y value we are having, tau 0 value we are having, and find d, and rest is same as previous problem. Okay, let's move to the third problem. If you have any doubt, then please comment and let me know. If you like the video, then to tell me. Okay, so let's move to the third problem. Okay, so this is the third problem and last problem for today's video. Actually, I like this problem. The reason is it is application based problem. Okay, and when it is application based problem, it is easy to teach, very easy to teach. Okay, just kidding. Okay, let's go move to the problem. Design a closed coiled helical compression spring used for a boiler safety valve, which is required to blow steam at the pressure of 1.5 Newton per mm square. Alright, so here we having one boiler, okay, and it is having like we can say like boiler means steam pressure, like, so it is having steam pressure from this side. Here is one safety valve and it is set for 1.5 Newton per mm square pressure. Okay, when the pressure is 1.5 Newton per mm square, it will just blow off and steam will go out. Okay, so now next problem reads the diameter of the wall is 50 mm. So diameter of this wall is 50 mm and the initial compression of spring is 40 mm. and the lift is limited to 20 mm. So what is meaning of this initial compression of spring and lift is limited to 20 mm? Okay, so now in this condition, when this steam is accumulating over here and it is not up to 1.5 mark, that condition, this spring is in compressed state, means it is already applying some force over here. Why? Because first that spring was like this, it has free length up to here. Okay, we compressed it and we made like this. So this was initial compression. So at free state, when there is no force, it was like this. We compressed it and we made like this. So now it is exerting force on this wall. Okay, so this initial compression is 40 mm. Okay, and the lift is limited to 20 mm. When it will blow off, when we having pressure as 1.5 Newton per mm square, then how much lift, how much more it can get compressed? So it can get compressed up to 20 mm more. So the final step will be like this. Okay, so initially it is compressed, so it is exerting pressure or force over here, and when this pressure exceeded this value, it will compress the spring further, okay, to 20 mm. Alright, now the number of cycles of load are expected to be about 10⁵. The material for the spring is chrome vanadium steel, for which the strength of values are given. Sigma u is given, sigma ys is given, g value is given. Use static approach. Okay, now they have told to use static approach. Okay, so first of all we have to find the value of maximum and minimum force, because it is not given in the problem. So now pressure given 1.5 Newton, number of cycle 10⁵, dV, that is wall diameter, is 15 mm. So this is the pressure and it is acting on this diameter. Okay, so force is nothing but pressure into area. So we can find the force. So initial force, we will get initial force. Okay, so initial force will be this pressure into area. Now G is given, initial compression 40 mm, initial compression of spring is 40 mm, lift is 20 mm. Now maximum minimum spring forces. Alright, so when we having P1, we just considering P1 as initial spring force. When this wall is just begins to blow off, means it is compressing this, it is just started to compress the spring furthermore. Okay, so it is P1. So P1 we can find out area. So P1 is equal to area of the wall into pressure. So area is given as pi/4 dV square, diameter of wall, into pressure. So diameter is 50 and pressure is 1.5, and you will get value as 42945.24 Newton. Okay, now at this pressure, the delta value will be, we know the delta value. So delta value, I am just considering it, that is 40 mm. So it is initial compression of spring, it is given initial compression of spring 40 mm. So what will the final compression? So that is delta 2, that is 40 mm plus lift of 20 mm. So finally 60 mm. Let's guess P2 is equal to force on spring when wall is fully open. Okay, then we know that force is proportional to delta. So we can say that P1 upon delta 1 is equal to P2 upon delta 2. We are having P1 value, delta 1 value, delta 2 value. P2 you can find using this relation. Just put the value of P1 over here, that is 2945, delta 40, and it is 60. You will get P2 value as 4417.86 Newton. So this is the required value. Now they have already told use static approach, so you don't have to use varying approach. First of all, they have mentioned static approach, so it is, this term is not for varying design of spring for under varying load. It is under static approach. Okay, so you having the maximum force, so this is nothing but P max. Okay, so you're having maximum force, use static approach and solve the remaining problem. Okay, so now you don't have to consider this as a P max and P1 as a P min. No, you are using static approach, means only one force, means only P2, that is maximum force you're going to consider and solve the remaining problem using static approach. Okay, so we are stopping here only. So hopefully you are understood the design of spring for varying load. Okay, just let me know, comment and tell me whether you are understanding these video lectures or not. Okay, thank you.